suppose V1 through Vn is an orthogonal set or list of vectors. Suppose you have V1 through Vn, that's an orthogonal list of vectors, which means anything besides itself would be dotted as 0, dot product as 0. And I should say non-zero vectors. Because if it's a 0 vector, then any list with a 0 vector will automatically be not linearly independent because the list will become redundant. Right? So linearly independent means that when you try to express a span of these vectors, you can't have a smaller list that would have the same span. Okay? That's another way to think about linear independence. Right? Okay. Then this is linearly independent. So let's try to prove that. Proof. Suppose C1 V1 plus C2 V2 plus da 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 Cn Vn equals to 0. Now the textbook definition of linear independence is that if this ever equals to 0, linear combination of the vectors equal to 0, what must be true? The C1 has to be 0, C2 has to be 0, and the Cn has to be 0. Everything has to be 0. That's the only way you can have a linear combination equal to 0. Okay? If that's not true, then you can easily see that this won't be a non-redundant list. Okay? This list will be redundant if there's something else. Okay? So I want to show that every CK is 0. So do this. Then V1 dotted with C1 V1, and to make it more general, let's use, because this should be true with respect to any inner product, not just the standard dot product. If you have V1 dotted with this entire thing, since we claim that this is given as, we are assuming that this is equal to 0, we just have V1 dotted with 0, or inner product with 0, and anything inner product with 0 by linearity, this has to be 0, right? But here's another way to do it. Using linearity, it'd be like that, right? So you have V1, C1 V1 plus V1 C2 V2 plus da 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 V1 Cn Vn equal to 0. And then if it's a real inner product, then C1 through Cn's are real values, then they just come out, right? If it's a Hermitian inner product, what happens? If it's Hermitian, then what happens to C1? Because Hermitian has like an extra bar, conjugate, complex conjugate in the second element, right? So these will go through a conjugate. So when they come out, it will be C1 bar, V1 V1. C2 bar, V1 V2. Cn bar, V1 Vn equal to 0. But then we assume that all these are orthogonal, right? It's orthogonal with respect to this inner product, so those are all 0. The only thing that's non-zero is what? This is what? This is v1 norm squared, right? Anytime you do an inner product of a vector with itself, it's the norm squared. So you have c1 bar times a non-zero thing equal to 0 vector on the right side. Okay. Actually, no, this is not 0 as a vector, it's 0 as a number. This is 0 as a vector, but if you do an inner product, it's 0 as a number. Okay. And these are two numbers. And because this is non-zero, we can divide by the same thing, norm squared. We get c1 bar equals to 0, which means c1 is 0 bar, which is 0. If you just take the bar both sides. Complex conjugate of the complex conjugate is itself. And by the way, if this is in a real vector space, you don't need all these bars. So anyways, you have this. So we just proved that c1 has to be 0. Now, in order to prove c2 as 0, what should you do?
The inner product with v2.
Yeah. Now, do the inner product with v2. It goes to the same thing, except that the last survivor will be the second one, c2 bar v2 norm squared. So everything here will be 0 except for c2 times v2 squared, and then do the same reasoning, you get c2 as 0. So continuing in this manner, we have c1 equals to 0, c2 equals to 0, all the way up till cn equals to 0, which is the definition of linear independence. All right?